All right. Assalamualaikum warahmatullahi wabarakatuh, and very good afternoon for those who are in Malaysia, and very good morning, I suppose, for those who are in the UK, and wherever you are. Welcome to Distinguished Lecture Series (DLS) event organized by Faculty of Engineering, University Technology Malaysia (UTM). So this is now the 33rd event of DLS. My name is Ahmad Razin, a senior lecturer in UTM. So your host for today. And we are very fortunate and very glad today to have a professor from Imperial College London. For our guest, for speaker for today, that is Professor Bassam Izzuddin, a engineering Imperial College London. Okay, he was actually my PhD supervisor in 2008, 2012, and I would describe him as a very knowledgeable supervisor and also a dedicated one, because I still remember sitting with him until quite a late night solving a problem with my programming codes, all the debugging things, and then at that time I was stuck with the programming. I think about 1 or 2 weeks, and then he said to me, we need to get to the bottom of this. And that sound, I mean, I know that sound because it seems to me I need to stay with him until we manage to solve the problem. And we did, I think, after several hours, 3 to 4 hours, I think. And then we solved the problem. And the point that he wanted me to learn is that whenever next time in future, whenever you're stuck, you should be able to, to relax, to manage yourself and take time, and then just go back and then lesson that I learned from Prof Bassam, and thank you very much, Prof Bassam, for that. Okay, this is the session for Prof Bassam, and I think he will talk about a topic on high fidelity modeling of large scale structures under extreme loading. And without further ado, I would like to invite our Dean, Professor Dato IR Muhammad Rafiq, to briefly introduce our distinguished speaker today. Over to you, Prof.
Thank you, Razin. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Welcome everyone to our 33rd UTM Engineering Distinguished Lecture Series. My name is Muhammad Rafiq and I am the Dean of Engineering, University Technology Malaysia. Today, it is my utmost pleasure to welcome Prof. Bassam Izzuddin from Imperial College London. A bit about our presenter today. Bassam Izzuddin is Professor of Computational Structural Mechanics and heads the CSM group at Imperial College London. Since joining Imperial in 1990, he has developed advanced nonlinear analysis methods for structures subject to extreme loading, and he has engaged in national, international collaborations with industry and fellow academics on applied structural engineering research utilizing his program Adaptic. Besides major developments in detailed modeling, he has also developed a range of simplified analysis methods, which are currently being applied in design practice for offshore and building structures. He has supervised over 40 PhD students to completion, and his publication record exceeds 250 papers in leading international journals and conferences. So that is a biography of our speaker. Here now is Professor Bassam Izzuddin from Imperial College London with a talk entitled High Fidelity Modeling of Large-Scale Structures Under Extreme Loading. Professor Bassam Izzuddin, over to you.
Thank you, Professor Rafiq. It is really my pleasure to be delivering this lecture at your invitation today. And before I start, I should say that it was a delight to supervise Razin. Even as someone who did not have a background in finite element analysis when he came to Imperial College, he really did extremely well to build up the background, but not only that, to progress and do very exciting things in mesh-free analysis and advanced computational modeling. So it was really my pleasure to act as his supervisor at that time. To the current topic of my lecture, I'll be talking about high-fidelity modeling of large-scale structures with particular emphasis on the nonlinear response under extreme loading conditions. And just to provide a bit of a context for what I mean by large-scale structures, these are the types of structures where obviously they are large in the sense of the extent of discretization or detail that needs to be considered, but also where you have interacting parts that are too complex to deal with in isolation. So examples of these would be, for example, offshore jacket structures, which may or may not be linked together, subject to wave loading or subject to earthquake loading, where you actually need to model the whole system together and consider the nonlinear effects. Another example could be a cable-stayed bridge subject to perhaps earthquake loading. But also, the types of structures which require detailed modeling are those that are subject to earthquakes, for example. I mean, obviously, this is what I'm showing here is an extreme case, but when you are considering a structure under earthquake loading, you have many interacting parts, and depending on the scale of the structure, you are talking about significant computational sophistication and demand that would be required. I'm showing here also a small building. This is a masonry kind of structure, and it might look to be a small-scale structure, but in fact, computationally, this is a large-scale structure if you are going to consider the modeling of individual bricks as computational entities. So quickly, the computational demands that are required to deal with this kind of problem become very excessive, as I will highlight later. So this is really the context of the lecture that I'll be talking about, and I will precede the methods that I'm going to talk about. I precede this with some background on developments that we have done at Imperial College in nonlinear finite element analysis. Finite element analysis, as many of you would appreciate, is a kind of approach that has been evolving over many and many decades, whether it's linear finite element analysis or nonlinear finite element analysis. So I cannot pretend to cover all developments in nonlinear finite element analysis in a very brief lecture here. I'll be focusing on the highlights of work that we have done at Imperial College in support of modeling using nonlinear finite element analysis. And I will start by talking about what we call one-dimensional beam column elements. These are the types of elements that you would use for modeling individual beams or columns. In our case, because we are interested in extreme loading, such elements need to consider both geometric and material nonlinearity. By geometric nonlinearity, we mean modeling stability effects or modeling the effects of large displacements. And by material nonlinearity, we mean the modeling of the nonlinearity that arises from the material exceeding its linear range. For example, steel, when it yields, it exhibits nonlinear behavior, and concrete is inherently nonlinear in compression, and also when it cracks in tension, it also becomes highly nonlinear. So we are talking about elements that can deal with both geometric and material nonlinearity. More specifically, we have done some leading research on a co-rotational approach that allows to model the influence of geometric nonlinearity in a relatively straightforward way. That is based on what is referred to as the co-rotational approach. And we have enhanced this with adaptive capabilities for elastoplastic analysis. I'll show an example in a minute. But also looking at thin-walled members where the influence of warping effects, of thin-walled steel sections and so on become very important. And significantly, the kinds of elements that we are talking about are applicable to both steel and reinforced concrete members. So within this context, I'm showing here a video of which illustrates the adaptive capabilities that we have been concerned with. So this is an example of an offshore jacket structure where these red bits that are being shown are basically showing the adaptive introduction of expensive elastoplastic elements. So initially the analysis started with one elastic element per member, and during analysis we introduce more expensive elastoplastic elements only when and where necessary, and that we have shown that saves 90% of computing time without really compromising the accuracy of the analysis. So so this is some background on 1D analysis, and then I'll show you an example of 2D developments that we have undertaken as well, including again geometric and material nonlinearity effects. So again, utilizing the co-rotational system, we have developed a novel approach by which this can be done. And importantly, these kinds of elements are applicable to composite slabs, for example, reinforced concrete slabs, as well as laminates, for example, modeling glass facades and so on, where laminations are an important aspect of the structure, and also the modeling of curved shells. This is an illustration of a novel kind of element that we have. Sorry, let me just show it again. It's a novel element. It's a 2D element, but it can capture what we call the geometric orthotropy that exists with composite floor slabs. So it involved the extension of the conventional Reisner-Mindlin hypothesis, so that you can look at the influence of the ribs and so on. Okay. And this is an illustration of the use of this element with fire analysis capabilities. So looking at this is actually a representation of a substructure from an actual large-scale test that was undertaken at Cardington, and we can model the coupling of the one-dimensional beam column elements with two-dimensional composite and reinforced concrete slabs under fire conditions, and this shows what is happening as the fire load is introduced in the structure, and we got very good comparison against the experimental results. And finally, just mentioning 1D, 2D, there is also 3D solid elements, which we tend to use for modeling masonry structures in the main, where we model individual bricks with 3D solid elements, and then we model the mortar with two-dimensional interface elements. This is a very sophisticated capability that has been instrumental in some very recent research that we have been undertaken in different contexts, including the modeling of masonry arch bridges, as I'm going to discuss later. So besides also the element technology, which basically, as I said, 1D, 2D, and 3D elements, we have also been undertaking some advanced developments in nonlinear solution procedures, including some advanced arc length control methods, adaptive time stepping, and more recently, energy consistent dynamic contact analysis. Again, there isn't really the time to go into these in any great detail, but I'll show you here an illustration of the dynamic contact analysis, showing, for example, the impact of a sphere on a flat surface, and realizing an accurate kind of representation of the impact of such a sphere on the flat surface with I would say large time steps, which allow you to have a good computational efficiency. So this is some context. This is some background in terms of developments that we have been undertaking in our group at Imperial College. The main challenge really that we had to address relatively recently is the computational demand of these sophisticated high-fidelity models that arise even in the modeling of a simple problem, like in this case, a single-leaf masonry wall. This single-leaf masonry wall requires the use of 48 by 48 brick elements with interfaces. So if you are modeling individual bricks and individual mortar joints, that's what you would have. And just this single wall would require around 3 gigabytes of memory, and it would require around 2 hours for 10 load steps. So really, we are talking about a significant computational demand even for such a simple structure, let alone if you want to model, a whole masonry building, for example, under extreme loading with all the interactions between the different wall components and so on. And this is also another example of a masonry structure. So you can imagine that if a small wall requires such an amount of memory and computational demand, you can imagine the kind of requirements that these structures would actually pose. And indeed, you would quickly realize that there isn't enough memory in conventional systems to accommodate the memory demands of such structures. Leaving aside the issue of computational demand, the memory requirements are quite huge, and they would typically pose what we call a memory bottleneck. So we had to look for another way of modeling such structures beyond the conventional approach. And that's where we looked at high-performance computing as an opportunity to take our kind of work further so that it can be applied to large-scale structures. And just to illustrate the idea, when we talk about high-performance computing, if we focus on a compute node, or as you would know it, let's say a PC, it would have a few processors, typically not many, and then each processor would have also some cores. So effectively, you could benefit from running things in parallel on a compute node. But still, a single compute node has a restricted amount of memory that can be used. The opportunity that we saw is with high-performance computing, when you include several compute nodes and you put them to work together in a private network. And that is really a very scalable process, and you can add as many compute nodes as you want in principle. And then you can enhance the amount of memory and the computational resource that is at your disposal. Indeed, one can go even beyond the private network and think of the grid, where you might consider different clusters effectively talking to each other via a public network. So this is what we call a scalable and hierarchic distributed memory and computing power system. So in principle, therefore, we have the possibility of using many compute nodes and getting them to work together, giving us basically, in principle, unlimited memory and unlimited computational power. However, there is a particular issue that one has to be aware of, which is the increasing communication overhead as you go up this hierarchic diagram that I'm showing you. Basically, communication between the cores and processors within a single compute node is quite effective, quite fast. But then when individual compute nodes have to talk to each other, there is a significant communication overhead. There is a potential delay in communication. Now, that would not be an issue if each of these processors or compute nodes are working independently and on a process that does not need to know about what is happening in other compute nodes. But that's not really the case with modeling structures, where the individual parts of the structures are actually need to know about each other so that you satisfy equilibrium and compatibility. I'll talk about this in more detail later. But in principle, that is the kind of framework that we considered as potentially giving us a very exciting opportunity to scale our kind of approaches so that they can be applied to large-scale problems. So one way in which high-performance computing can be used is to adopt what is called conventional procedural parallelization. So if you have like a subroutine or a procedure or a function, and that involves many loops and so on, you could actually parallelize these loops. That's what we would call procedural parallelization. But procedural parallelization is more suited for what we call shared memory situations. So such an approach would have issues with memory scalability. You can do it at the level of a compute node, procedural parallelization, but it's not really suited for communication between different compute nodes. So you are really restricted often to shared memory systems, and you don't have you don't have the benefit of scalability of the memory, and it does not really map well to the hierarchic kind of structure of high performance computing with distributed memory. So what we did recently over the past few years is we developed what we call a hierarchic partitioning approach. And I will illustrate this with reference to the simple single leaf wall that I have shown you before. If we take this single leaf wall and then consider how we might actually analyze it, making use of multiple nodes and multiple processors, then potentially we can divide it, say, into 4 partitions. And then each of these partitions would be run or would be analyzed on a separate processor. The problem is you still need to ensure that these partitions are compatible, that is, the displacements at the boundaries of these partitions are compatible, and that equilibrium is also satisfied at the partition boundaries. So the individual processors would actually ensure compatibility and equilibrium within the partitions, but you need something else to ensure compatibility and equilibrium at the partition boundary. And that's the role of another process, which we call the parent process, that would collect information from the individual processes representing the partitions and make sure that what we are getting at the partition boundary is in equilibrium and is compatible. But not only that, we can actually take these individual partitions, what we call child partitions. So this would be the parent process, parent partition, and these would be child partitions. We can take the child partitions and divide them further into their own child partitions. So in this case, we divide each child partition to 6 child partitions. And you can imagine now a hierarchic kind of framework or a hierarchic structure for the partitioning. And that actually maps very well to what I showed you before in terms of the hierarchic structure of high-performance computing. So, for example, we can run the whole of this partition with its children partitions on a single node, and communication here would be very effective, very cheap. And similarly, we can run the next set of partitions on another node, and so on. So the communication would be very effective. The only communication across the nodes would happen at the level of the parent structure when we are collecting information about the top level 4 partitions. So that is really the idea. And how we implement it is by using the concept of what we refer to as a super element approach, or a dual super element approach. So by example, let's say we want to partition this structure into 2 partitions. We have several possibilities. The first one is to simply take the nodes where these partitions are going to interact and consider them in a parent structure. And then we have 2 super elements, one representing the partition boundary in this leftmost partition, and another one representing the partition boundary in the rightmost partition. So we have 2 super elements in the parent structures, in the parent structure, and then each of these super elements would be responsible for collecting information from its respective partition at that child level. So that's one approach. Another approach would be to say we'll take the nodes at the partition boundary, but at the parent level, we will have just one super element dealing with the child partition, and then the remaining interior nodes would be considered at the parent level. So there is no problem with us including the super element that represents the child partition, as well as conventional finite elements. And that is also a possibility. And obviously the other possibility is to make sure or consider that the parent structure is the one that involves the larger partition, and the super element refers to the smaller partition. So that's really the concept. Effectively, child partitions are represented in the parent by placeholder super elements, and the parent and child partitions are, importantly, they are processed in parallel. I'm here showing just a single level of partitioning, but the same concept applies to hierarchic partitioning as well. The idea is that the parent structure, or the parent partition, is responsible for ensuring equilibrium and compatibility in the child partitions at the partition boundaries. And then the individual processors would be responsible for ensuring equilibrium and compatibility within the partitions of the respective child partitions. And parallelization is then achieved via communication between placeholder and dual super elements. So effectively, the dual super element is considered on the child partition side. It's a shadow of the parent super element, collects the freedoms on the partition boundary. And basically, this kind of approach allows us to recover easily the condensed resistance forces and stiffness matrix on the partition boundary using the frontal method. This is the only equation I'm going to show you. This is illustrating what you have to do at the partition level, at the child partition level, to ensure that you satisfy interior equilibrium and compatibility, but also feeding back the forces and the stiffness matrix at the partition boundary to the parent, so that you can ensure, so that the parent can ensure equilibrium and compatibility between the different partitions. So let's say at some point within the child partition, we are always considering what we call out of balance forces within the child partitions. This is vector G. And we are always looking to correct the interior displacements. This is always what we have to do in nonlinear analysis. So we are looking to correct the displacements within the partition, but also on the partition boundary, using the tangent stiffness matrix. So we are always looking to solve a system of equations which is K times delta D equal to G. The only thing is this kind of representation involves not only the interior freedoms of the partition, but also the freedoms on the partition boundary. And obviously, when we are processing the child partition, we don't know yet what the displacements are, what are the corrections of displacements are on the partition boundary. So effectively, what we do is we perform forward elimination, effectively allowing us to determine the condensed tangent stiffness matrix and the condensed resistance forces. Effectively, the condensed tangent stiffness matrix is then fed to the parent structure. And at this point, the child partition is always waiting at this point. It is waiting for the parent structure to tell the child partition what the iterative displacements, these delta D at the partition boundary, what these are. So it receives these from the parent structure. Then it follows a backward substitution process to determine the incremental and iterative displacements within the interior of the partition. And then we follow this by determining, now that we know the incremental or the iterative displacements on the partition boundary and within the partition, we can now form the full tangent stiffness matrix and the out of balance forces, and follow this again with a forward elimination process that gives us the condensed tangent stiffness matrix and the condensed resistance forces. So basically, this is the process. We are always, the child partition is always waiting at this point to receive the iterative displacements at the partition boundary, follow this with backward substitution to determine the iterative displacements within the partition, form the tangent stiffness matrix and out of balance forces, and then perform forward elimination. And this really offers a way of upgrading existing finite element programs relatively easily with the concept of introducing a new super element. So in a finite element analysis program, you typically add conventional elements, yeah? And that is relatively easy. This idea that we have introduced is basically the idea of introducing a super element, which can be treated much like a conventional finite element, except that if you want to determine the tangent stiffness and the resistance forces of this super element, it's not done within the same process, it's done in a separate child process. And that makes it relatively straightforward to enhance existing finite element analysis programs. And indeed, that's what we did with our program with Adaptic. We have enhanced it with this approach. And what I'm going to show you now is several examples that illustrate the benefits of this approach. I'm going to show you examples from reinforced concrete structures, from steel structures, as well as from masonry structures. And I start with a reinforced concrete building subject to earthquake loading. This is just an illustration. It's an irregular 4-story reinforced concrete building where the beams and columns are modeled with one-dimensional elements. The floor slab is represented in this case in a simple way with basic diaphragms, and we are considering geometric and material nonlinearity. And this building is subjected to an earthquake seismic excitation in the 2 horizontal directions. I should have noted here these points P and Q. These are points where we are going to measure the response and then compare between the different approaches. So the structure is subjected to an earthquake in the X and Y directions. And we consider 3 different computational models for comparison purposes. The first model, model A, is the conventional one. It's the monolithic model, which you would run on a single processor. So it's one process. The second one is a partitioned one. So we have 4 child partitions and a parent partition, as we said, to ensure equilibrium and compatibility between the different partitions. So that means 5 processes or 5 processors, and model C is 14 child partitions. So each floor, like here, floor 1 is subdivided further into 4 partitions, and floor 3, it only has 3 partitions. So in total, we have 15 processes. And what's important to note first is that all these models, whether it's the monolithic model or the partitioned with 5 or 4 partitions and the partitioned with 14 partitions, all of them give the same results. These are the displacements in the x direction at point P, displacement in the y direction at point B, and so on. This is the same at point Q in the x direction and in the y direction. So all these models give the same results, but in terms of computing time, we notice that the monolithic model takes 13 hours, 37 minutes. The partition model with 4 partitions takes 4 hours and 45 minutes. And the partition model with 14 partitions takes only 30 minutes. If we look at the speed up, that is the ratio of the time taken by the monolithic model to the partition model, the speed up is roughly 3 for partitioned model B and 27 for partition model C. Typically, you would not expect the speed up to be more than the number of processes that you are using. You would not expect this to be more than 14 or 15, but we are getting 27, and that must have also some reasons behind it. The reason is that the solution of the system of equations is based on the frontal method, and with monolithic model A, the front width is 318. It actually increases a little bit with partition model B, but when we go to partition model C, the front width has dropped significantly to 198. So not only are we benefiting from increased processing power, we are also benefiting from a further reduction in the computational demand of the frontal solver, and that is effectively, we are achieving an effective implementation of what is referred to as the multi-frontal solver. There are multi-frontal solvers. This is like a simulation of multi-frontal solvers using partition modeling. So clearly, the benefits are tangible and very significant. If you can run the analysis 27 times faster than obviously for a large scale structure, that is obviously an important benefit. This is an application that we have considered and we have been asked to do in Sicily by ANCE, Catania. ANCE is it's like an association it's a national association of construction in Sicily. They asked us to consider the seismic vulnerability of the buildings in Catania, which has many buildings that are not designed for earthquakes, but they know that the city is actually prone to earthquakes. So the idea was to assess the vulnerability of their existing structures and then propose some retrofitting schemes for them. In this context, high fidelity modeling we have shown that it is actually crucial. And we considered a typical case study. We took a typical building in Catania. We used 31 partitions. This is an illustration of the floors, and each of the floors was divided effectively into 4 partitions. And we have conducted several kinds of nonlinear dynamic analysis simulations for them. A typical model, even with partitioning, takes 2 to 3 days. So you can imagine if we hadn't really done partition modeling, a conventional model would have taken several weeks for just a single run. So really, we are bringing nonlinear dynamic analysis, high fidelity nonlinear dynamic analysis into the domain of the feasible. Otherwise, it's not realistic to wait several weeks for analyzing a single structure like this. So these are now examples from steel structures. This is a cellular beam, which, by the way, Razin would be very familiar with, because that was the area of his research, even though he considered it using mesh-free models, not finite element analysis. But in any case, this is a structure which is actually quite amenable to partitioning, because we can take each of these individual unit cells and consider them as a separate partition. In this case, such cellular beams are susceptible. They are quite good, actually, because they give you enhanced rigidity, and they minimize the use of the material with the use of the holes. On the other hand, they can be associated with significant local instability, especially in the web post. So, and if you want to model this in great detail in the nonlinear range, then you have to use quite a few two-dimensional finite elements to model each of the unit cells. And, you know, by the time you have modeled the whole structure, you are talking about a significant number of degrees of freedom, in this case, 300,000 degrees of freedom. So we consider two kinds of partitioning in this case: a flat model where we have a parent structure and 33 child partitions, and a hierarchic model where consider a parent structure, 4 child partitions, and then each of these child partitions would have more or less 8 or 9 child partitions. All of these, the monolithic as well as the partitioned models give the same outcomes. These are displacements, total vertical displacements, and the web post lateral displacements. They all give the same results. And just to show you what kind of analysis and simulation we are considering here, this is looking at a single partition, and as the load is being applied downwards, if you focus on the right green partition and especially the web post, you will see what is happening as the load is being increased and the buckling of the web post. And indeed, we have several of these web posts experiencing buckling, especially towards the support. So it is quite a sophisticated capability that we have in this respect. And what I'm going to focus, what I'd like to focus on, is the influence of partitioning. So, for example, the flat partitioning and the hierarchic partitioning, they are associated roughly with a similar number of partitions in total, but bearing in mind that when you have hierarchic partitioning, you need to include some placeholder, if you like, parents, so that they can collect the response at the partition boundary. And that's why with hierarchic partitioning, we have 4 more child partitions. What is important to note is we have, again, significant speed up. This is now more reasonable than before. It does not exceed the number of child partitions. But what's interesting is that with hierarchic partitioning, we get 17, a factor of 17 for the speed up, whereas with flat partitioning, it's only around 13. So clearly, hierarchic partitioning in this case is 34% faster than flat partitioning, and it demonstrates the benefits of making use of the hierarchic structure of the HPC system in our hierarchic partitioning approach. And this is an example. This is also a steel cable stayed bridge, but also with reinforced concrete slabs. Here, I just want to highlight the modeling power of hierarchic partitioning. So this could be your parent structure. It might include the piers and the representation of the partitions for the cables and for the deck, the parents basically for the cables and the decks, and then the child partitions for the cables and the deck would define the cables, and perhaps parents for the slab, the slab elements. So basically, you can imagine how this actually can be quite useful, and these, for example, these child partitions are reusable, so you can use them in different parts of the structure, and that gives you significant modeling benefits as well. So just in a quick way, here, this is a hierarchic partition model with 69 partitions. It's run on 24 processors, because at the time we did this, we were limited by the number of processors that we can use. But nowadays we can use 200 or a lot of processors. We have quite a lot of computing power at our disposal. But at the time we only used 24 processors, and for 200 time steps this took 18 minutes, which is quite reasonable for such a large-scale model. And we have also applied this in the context of steel structures to an industry-funded project concerned with the development of all-steel sandwich panels. This project was funded by AMEC Foster Wheeler and POSCO from South Korea, a steel producer. And the application of high-fidelity modeling was really crucial in this case, because these structures are susceptible to localized buckling, and you cannot really capture this with anything other than having many elements, as we can see here. So just to show you the nature of the response that we are talking about, this is a typical response under uniformly distributed loading. So you reach a peak here where you start observing yield lines. Remember that there are cells underneath. So these yield lines do not just involve yielding of the material, but also local buckling, elastoplastic local buckling between the cells. Point B here is where we start experiencing also local buckling effects at the corners. And point C, when we start picking up and developing membrane action, we can also start observing perimetric local buckling because of hoop effects. So, as you can see, it's quite a complicated kind of system and response that we need to capture. And the way we do this with partition modeling, as we've discussed before, is to partition the structure and consider running it on several processors. Here we consider different levels of partitioning, varying from the monolithic to 25 partitions to 64 partitions and so on. And we achieve, if the monolithic time is 100, then with 25 partitions, we reduce the computing time by roughly 75%. So this is, again, a very significant reduction in computing time. And this is showing that 25 partitions has the optimal speed up of roughly 3.8. The final application area that I'm going to show here is masonry walls. This is the original wall that I showed you before, just to show the influence of flat partitioning and hierarchic partitioning. Again, in this case, as you can see, flat partitioning achieves some good speed ups, but hierarchic partitioning is much more effective. And that is obvious from this figure, where the speed up from flat partitioning is roughly around 7, whereas with hierarchic partitioning you can achieve a speed up of around 13. So, the potential for hierarchic partitioning is huge. We applied this to the modeling of wall structures, wall masonry structures under extreme blast loading. This is work that we published in the American Society of Civil Engineers. And these are the responses at different points, A, B, and C. The important point to make here is that we have used two-level hierarchical partitioning, 50 partitions, and each step takes a reasonable five minutes in this case. So the potential of hierarchical partitioning is obviously quite significant. The area where really this work has come into its own is in the modeling of masonry arch viaducts. This is an industry-funded project by Network Rail. The interest is on assessing the damage initiation and propagation under train traffic loading. High-fidelity modeling is crucial if you want to observe the the propagation of cracks between the masonry and so on. We have models for the backfill, continuum models for the backfill, the models that I've described before for the masonry, modeling the bricks and the interfaces, and suitable material models for these. This is just an illustration of a case study. It's a 3-span segment under train traffic loading with automatically generated partitions. We have considered analysis with the sophisticated mesoscale models and some approximate macroscale models. And you can see some difference between the mesoscale models and the macroscale models, not only in the serviceability condition, but significantly also under ultimate conditions. So this highlights the importance of really doing detailed mesoscale modeling. That's what we call this detailed approach for modeling masonry structures. The models that we have developed, and we are currently validating them against monitoring data from actual masonry arch bridges. This is a continuation of the project funded by Network Rail. And just to show you that we get, there aren't any models of this sophistication and of this computing power that exist anywhere in the world. We can model ring separation. If your arch is composed of different rings, then we can model the ring separation and the sliding of the rings against each other. And we can also model the detachment of the ring from the backfill. And just to say that we do not even dare model this problem with a monolithic model, because the memory demands, leaving aside the processing demands, the memory demands are prohibitive. You cannot run it on a single machine. And therefore, the only prospect for modeling this kind of problem is with partition modeling. So in conclusion, partition modeling on high-performance computers offers a realistic prospect for nonlinear analysis of large-scale structural systems, achieving significant speed up, but importantly, overcoming memory bottlenecks that one would face when modeling large-scale structural systems. The dual super element concept that we proposed, it enables hierarchic partitioning, which maps really well to high-performance computing hardware. It offers a significant reduction, therefore, of inter-node communication in the overhead for that. And importantly, it offers a way to implement this easily within existing nonlinear finite element analysis programs. And I've shown you several examples which illustrate the resulting capability, powerful capability for high-fidelity nonlinear analysis of real problems. And by this, I end my lecture. Thank you.
All right, thank you very much, Prof. Bassam. I'm glad that my work is in the slide. So at some point, it brought me back to Imperial College. Really misses that environment. Okay. Anyway, we have a very limited time for Q&A, and I think I would allow for several questions from audience. If you have, you can comment in Facebook and also YouTube. By the way, Prof, the fidelity modeling, is it a common word, or you propose the
high fidelity modeling? I would say it is it's an American term that arose especially after the World Trade Center events, and people started using this term as trying to model the details of what happened and so on. I mean, it existed before, but it's really an American term. And just so that we don't really use our own kind of words and maintain consistency, we use it. But effectively, what we are saying is the detailed modeling to the level of detail that is required to achieve a reasonable estimation or a reasonable representation of the true response of the structure. And this is the kind of level of detail which you would need for example, the masonry arch bridges that I've shown you. You cannot model these with a continuum model. And it's the kind of detail that you need for example, the sandwich panel systems. This is a it's a very detailed model that you need to capture all aspects of buckling and so on.
But it's not very specific to the partition model.
No. High fidelity can be done monolithically, okay, but can be done in a partitioned way. So here the general topic is about high fidelity modeling, and then the partitioning work is how we have managed to perform high fidelity modeling in a computationally efficient way. I did not include partitioning because I did not want to make the topic, too complicated and too technical.
Yeah.
So.
Okay, so we are still waiting for question if there is any. And then about the new, HPC, I think nowadays the high performance computing is very well developed, right? So is there any, future, works on HPC, or do you consider any?
Yeah, HPC is the hardware platform. Yeah, when you say high performance computing, it is the hardware platform. But there is a lot of potential work that can be done on partition modeling, on making it better. We're looking at contact analysis now with partition modeling, contact between different partitions. You might, if you are trying to model the collapse of a building, and you are partitioning it, but then one part can impact on another part. So there are issues there that need further research. So there is quite a lot of research that can still be done on partition modeling for high performance computing.
Okay, I think there's no question from audience. The topic is very inspiring.
Okay.
Anyway, just was one last question. I think about the partition. Then when you decide the partition, and you said about the automated partitioning, right? Is there any detailed work on how partition should be the most effective?
Generated. So that's a good question, and that's another area which we are working on, because you want to come up with partitions that offer you the optimal kind of distribution of computational demand, and give you the optimal speed up without really having to try too many partitions. Yeah, you cannot afford to be running every time, trying many different partitions every time you want to model a real structure. So we are working on this to try to come up with schemes that give us close to optimal partitioning in one go, rather than to try different levels of partitioning. Okay.
All right. Okay, there is one question. So this will be the final question, I think. Mr. No, I'm wondering the kind of structure to be able to live under the sea. Do you have any comment on that?
What kind of structure are we thinking of? Structures to live under the sea. Firstly, that's a technical challenge to come up with such structures, to also provide all the necessary facilities for people to be able to live under the sea and so on. If these structures need to be considered as high fidelity structures under extreme loading, then these kinds of methods will be applicable to them. But I think we need to resolve that challenge first. And also we need to have the motivation to want to live under the sea. So once that is resolved, then these models can be applicable not only to structures above the sea, but also under the sea.
Yeah. All right, Prof. I think maybe 1 minute, if you can summarize your talk today.
So as I said, the partition modeling is quite an effective way to undertake high fidelity modeling of large scale structures, and without this we cannot really tackle many of the very important structures with current computational resources. So it is as I have shown, you need it at least to tackle the memory bottlenecks that would exist if you try to model real structures with high fidelity.
Okay, so on behalf of the faculty, I think I would like to thank Professor Bassam Izzuddin for his very inspiring talk. So I think we let the session finish. So thank you very much, Prof.
Okay, thank you, Razin, and thank you, Professor Rafiq.
Thank you, Razin, for chairing the session, and thank you for introducing Professor Izzuddin to me. And to Professor Bassam Izzuddin, thank you very much for accepting our invitation to speak at our distinguished lecture series. Just want to tell you that, you know, I spent close to 4 years at Imperial College, actually working on the finite element modeling of hip implants under the supervision of Professor Andrew Amis. So, you know, back then it took something like days just to perform a simple analysis of a hip implant. Later on, when I become a supervisor myself here in UTM, they with the super fast computing facilities that we have, the things that took days during my PhD years at Imperial College now take something like hours. You know, they can complete the finite element mesh, finite element analysis that used to take something like days in my years for my PhD. They took something like just hours. So it is amazing the kind of computational speed, computational power that we have nowadays. So again, Prof. Izzuddin, thank you very much for accepting our invitation. And to all of the viewers globally, thank you for watching UTM Engineering Distinguished Lecture Series. We have many more lecture series for you. So until then, bye for now. Bye-bye, everybody.
Thank you.
Bye-bye.
Thank you. Bye.